Welcome everybody. It's a pleasure for me to present you my PhD work on enhancing the smart digitized food supply chain through self-learning and self-adaptive systems. My name is Elia Henrichs and I work as a research assistant at the University of Hohenheim. So when we talk about the food supply chain, we mean all stages of a food product, from the production site, which is often a farmer, to the consumer. And as you can see, there's many paperwork done in between these stages, which will be delivery notes or certificates. And of course, there is some digitalization in the food industry, but the data are often not shared and only stored in clouds. Our focus in the food supply chain is on the food quality. The quality analysis is mainly done at the manufacturer or processing stage. Of course, before the producer and supplier will have a quality check as well. But at a manufacturer, the food quality can be lastly adjusted before going into retail. The next quality control will be at the consumer side. The consumer will have a look at the best before date, he will taste and smell the food. And if the food is good, the consumer is happy and he will enjoy the food. But if there's something going wrong and the food is not good anymore, or even worse, it's spoiled or faulty in another way, the consumer could become sick and won't be happy anymore. And what will the consumer do? The consumer will contact the retailer and manufacturer and complain about the food quality. And the manufacturer and retailer have to go step by step through the supply chain to find the stage where the food got damaged. As you can imagine, this is very time consuming and expensive. Additionally, it's really complex to identify those errors, and all the actors in the food supply chain are always dependent on the other actors. So they aren't protected from any data manipulation. How can we improve the transparency in the food supply chain? Therefore, we plan to apply the blockchain technology, which is known from cryptocurrencies like Bitcoin. You can imagine the blockchain as distributed ledger between the participants in the food supply chain. So it's decentralized and there's no central trust authority needed. Every entry or change is getting logged and validated through hash functions, so the data in the blockchain is nearly not manipulable and really transparent. Further, all the actors in the food supply chain share their data directly and can get access to the data, which depends a bit on the blockchain architecture itself. There are examples of the blockchain technology used in the food industry right now, but as you can see, they are only used for traceability reasons. And most of the examples given are more showcases, and the blockchain technology is not used for all of their products. The consumer can trace the food as well via the blockchain using a QR code. So the consumer can trace this food easy and fast, as well as the processor or all the participants in the food supply chain. Additionally, this reduces the paperwork a lot. But in the end, if there's a food issue, the food is still wasted and lost. That's why we want to add real-time analysis and forecasting to avoid those critical conditions to the food supply chain. Therefore, we need novel sensors which are able to share and provide the data of the current food condition and quality, especially in those transportation steps or stages. The analysis could be either done via cloud, but due to latency or communication issues, this is more retrospective and not that much at real time. So the analysis should be done on the edge, the point of the data's origin. The food quality will be directly checked and logged into the blockchain. If a damage or spoilage occurs, the food should be easily identified and sorted out, so it doesn't get consumed anymore. It would be even better if we can avoid those critical conditions with the forecasting. That's why we want to add machine learning on the edge, so we can determine spoilage patterns, which is very complex, because the foods will vary naturally. And we need machine learning to reduce the energy demand of the sensors, because we don't know exactly how long a sensor needs to be alive. Which brings me to my research question. How can we intelligently combine those technologies? Therefore, we plan to apply the multi-level observer controller architecture from organic computing for the adaptation. I want to show you briefly on how this could be applied with two examples. As I said before, we will have an adaptive monitoring to ensure a long lifetime and high reliability of the sensors. And we plan to apply an adaptive best before date so the consumer can get easier and better access to the food quality. As you can see, we have different layers. The lowest layer, the layer 0, is the system under observation and control. So this could be the sensor sampling rate, or the sensor sampling, or the best before date itself. Above this layer, we have the layer 1, the reactive adaptation layer, which affects layer 0 directly. This could be the sensor status, so monitoring the remaining energy, or if environmental system changes occur, the sensor could be switched from inactive to active or raise the sampling rate. On the other side, this could be also the shelf life prediction to prove if the best before date is still accurate enough. Above layer 1, there's a second layer, layer 2, the reflection layer. Here we think about a sensor validation system to determine sensor faults or failures. And on the other side, this could be used to develop new prediction models or new patterns. And the highest layer is the layer 3, the collective layer, where the user can interact with the system, and this layer could also support cross-company communication and cross-product communication. This brings me to the current status of my PhD project. At first, we need to identify relevant and suitable technologies. We want to build a prototype, and therefore we need to choose hardware and software components, as well as an exemplary food, which would make it much easier. After that, we are going to conceptualize our software design, and we can start building our hardware testbed, where we can generate and gather some data and test different hardware setups as well. A big step will be the implementation of the software components, and finally we are going to evaluate our system. This should be done experimental, and we want to compare our prototype to a cloud setup. So, as I said, this is my first presentation of my PhD project, so I'm at the first step right now. And I want to conclude my presentation with challenges and possible solutions for them. So the main challenges, as I said, are the reduction of the energy demand, which we want to tackle with the adaptive monitoring. This is needed especially for the long sensor lifetime, as well as the energy demand of the HML. We need to determine different spoilage patterns, therefore we plan to use different machine learning approaches, which could also be combined. The prediction algorithms should be chosen dependent on the food, so you want to use machine learning approaches as well. Some minor challenges are to get data for our machine learning algorithms. Therefore, we plan cooperations with industrial and scientific partners. We need to choose the hardware components. As I said before, this could be done via comparison of different setups and structures, For example, thinking about the data transmission from the sensor to the blockchain. And we need this as well for the first challenge. The data transmission itself will be a challenge. Here as well we are going to compare different setups. We need to determine when and what data to send to the blockchain. And this will be another challenge. And last but not least, the sustainability is always a point to focus on. So this could be done using a circular instead of a straightforward food supply chain. So our smart and digitized food supply chain connects the blockchain as data storage and data share, novel sensors for monitoring, and edge machine learning for intelligent food systems like the shelf life prediction and adaptive monitoring. I would like to thank you for your attention.